And in this talk, we are going to talk about magnetic nanomaterial, magnetic nanostructures. Those are systems in which the magnetic properties are strongly influenced by the morphology. And we will see three different systems: pattern antidots, T-shaped nanostructures, and nanopillars. So let's start with the pattern antidots. Antidots are arrays of nanoholes in ferromagnetic thin fields. They were firstly prepared using alumina templates and depositing on top, as you can see here, and they were used as sensors, for instance, based on magnetoresistance. On this other work, the sensor is based on magnetoplasmonics. It is a work in which I participated, and we were measuring the magneto-optical spectra as a function of the wavelength. And you can see that when we fill the nanoholes with a polymer, the curve shifts because now the local refractive index has changed, and as a consequence, the plasmonic resonance changes in frequency. But you can see here also the limitation of alumina templates. The arrangement of the nanoholes are always hexagonal, and the long-range order can only be maintained up to a few micrometers. So typically you have different grains, different orientation of the hexagonal arrangement in an alumina. So nanolithography techniques must be used to have other arrangement, in particular square arrays. So with lithography techniques, we can obtain long-range order in wide areas, and so this nano antidotes array can be used as magnonic crystals, and they can still be used for sensing or for magnetic separation. In this case, you can see that they have used antidotes with a square arrangement of the nanoholes, and they have combined this with nanoparticles that were functionalized to attach to the species that we wanted to separate in a water solution. So you can see that the nanoparticles accumulate in some regions of these antidote arrays. So we want to study why the accumulation of the nanoparticle is not uniform. So we have prepared antidotes using focus ion beam. So we started with a thin film made of permalloy, or made of cobalt, or made of bilayers combining cobalt and permalloy, and we drill the nanoholes with gallium ions. The hole diameter is of the order of 40 nanometer, and we work with a square arrangement of the holes with two periodicities, 240 nanometer or 360. And you can see here, for instance, in the case of this bilayer with 20 nanometer of cobalt and 9 nanometer of permalloy, that the initial film, the continuous thin film, exhibit the loop in blue. And when we drill the holes, in this case with this periodicity, 240 nanometer, there was a strong hardening of the magnetic properties because the domain walls are pinned by the nanohole. So depending on the direction of the applied field, we obtain the black hysteresis loop or the red hysteresis loop. So we have used magnetic foam microscopy to understand this behavior. On the left, you can see the topography as in standard atomic form microscopy, simply the nanoholes. And on the right, you have the magnetic contrast. And please let me remind you that magnetic foam microscopy is a charge mapping microscopy. So the contrast is given by magnetic poles. So the bright and dark regions can be associated with magnetic poles. So before the experiment, we magnetize the tip in a known state, in this case, like this. So we have a south pole, which was closer to the sample. So when we have repulsive interaction, it means that we are having a south pole in the sample, and when we have attraction, it means that we have a north pole. So that's why we can associate bright and dark regions with south and north poles in this case. So you can see that in the magnetic contrast, there are some regions like this one, which exhibit a tiny contrast. And if we focus our attention on this unit cell, you can see that we have a bright region here, and we have a dark region here. So we have a magnetic moment that is pointing like this. And it's doing the same all along this row of unit cells. On the second row, however, the contrast has changed. Now the south pole is here, the north pole is here, so the magnetic moment is pointing like this, and it's the same on this second and third row. So this is the scheme of the magnetic state in this area. And in between the first and the second row, we have a low energy superdomain wall that is pinned by the nanoholes. But beside this zigzag tiny contrast that we see in many regions of the sample, we also have some other regions which exhibit a strong contrast that can be monopolar dark or monopolar bright or dipolar. It has high intensity, is a high intensity contrast, which means that they are accumulating a lot of magnetic poles. And we can analyze in detail those regions. So let's start with the dark one. So this is the scheme of this region, and you can see that there are two low energy superdomain walls that finished where the dark contrast region starts. And actually, all along this region, the magnetic moment are pointing along the same direction, and it is below the dark region where we have other orientation. If we now focus our attention on the bright region, you can see that this is the scheme. Again, we have two low energy superdomain wall that ends where the bright region starts. And in this case, we have a uniform magnetization on the left or on the right. So those regions with a strong monopolar contrast are called high energy superdomain walls because they are accumulating a lot of magnetic poles in those regions. And now, finally, the dipolar contrast region is composed of a bright region, of a bright high energy superdomain wall, and of a dark energy superdomain wall. So you can see the bright region, this 1, 2 low energy domain wall, and for the dark region 1 and 2. So at the end, we have 4 low energy superdomain walls in this region with 2 high energy superdomain walls. And now we can understand why, when this kind of antidotes are used for magnetic separation, the magnetic nanoparticles are accumulated in certain regions. Those are the regions which exhibit high energy superdomain walls, which exhibit high density of magnetic poles, and that's why they are trapped in those regions. So now let's switch to the second system, T-shaped nanostructure, and that was motivated by this theoretical work by 2 groups in Chile and in Brazil, and they proposed to use this T-shaped nanostructure to store 2 bits of information. One bit could be associated with the vertical branch of the T, pointing upwards or downwards, whereas the second bit could be associated with the magnetization in the horizontal branch, pointing rightwards or leftwards. So we did experimental study based on this. We fabricated using E-beam lithography these T-shaped structures. You can see the topography on the left and the magnetic state on the right. All these 4 T-shaped structures in this image are exhibiting the same magnetic state. Let me zoom. You can see that we have a bright contrast here, dark here, so the magnetization is pointing downwards in this vertical branch, and we have bright south pole here, dark pole here, so magnetization is pointing leftwards in the horizontal branch. And this is no surprise because they were imaged after being saturated, applying a magnetic field along this direction in an electromagnet. So the horizontal component of this in-plane field was towards the left, and the vertical component was going down. So, but the sample was imaged in a remanent state, so this state is quite stable. So we can use this code. We can associate a 0 when the magnetization is pointing leftwards in the horizontal branch, and a 1 when it's pointing rightwards, and for the vertical branch, a 0 when it's pointing downwards, and a 1 when it's pointing upwards. So this is the 0-0 state. This is the 0-bit X, Y, and Y state. If we now apply the field along this direction, and we remove it, the sample finishes in this state. The horizontal branch is still pointing leftwards, but now, as the vertical component of the applied field was upwards, now it has switched the magnetization of the vertical branch compared to this image. Now you can see the bright is here, dark is here, so now it's pointing upwards. This is the 0-1 state. And we can do the same now, applying this field. In this case, we are switching the horizontal branch. Now we have bright and dark. Now it's pointing rightwards. It is the 1-1 state. And finally, by applying this field and afterwards imaging in a remanent state, we have switched the vertical branch of the T. Now is pointing downwards. So this is the 1-0 state. So we have the experimental proof of the 4 remanent states that are stable and that can be achieved using this T-shaped structure. So they could be used to fabricate magnetic hard disks based on T-shaped nanostructure. And in this case, the recording head should be composed of 2 tiny electromagnets, one to apply the field along this direction and another one to apply the field along this direction. And in order to read the information, here we are coding the magnetization or the magnetic stray field using this color code. So we will need 2 sensors based in our reading head, 2 tunneling magnetoresistance sensors. One could be placed at the end of the vertical branch, so we can know if it is pointing upwards or downwards. And another one would be focused to measure the stray field coming from the horizontal branch. So it can be rightwards or leftwards. So, okay, now let's switch to the third system, magnetic nanopillars. In this case, they will be made in large area without needing a lithography technique, but using self-assembling processes in a sputtering. A sputtering is a physical vapor deposition technique. In a vacuum chamber, we have a target and we have a substrate. We introduce an inner gas, we create a plasma, and we accelerate the ions of the inner gas towards the target, and we eject atoms that are deposited onto the substrate. When we have this configuration, target and substrate parallel or quasi-parallel, what we obtain is a thin film. And many applications in our daily life have thin films prepared by sputtering, for instance, the hard disk of the computer, photovoltaic panels, or even the electrochromic windows in smart buildings. In order to have nanopillars, we need to tilt a lot the substrate with respect to the flux of atoms. By so doing, self-atomic shadowing processes take place that I will explain in a minute, and as a result, a nanopillar growth is obtained. The diameter of the nanopillar is of the order of 50 nanometer, and the length can be easily controlled with the deposition time. All these parameters play a role when we prepare nanopillars with sputtering. I don't have time to review all of them, so I will explain the most important ones. Let's assume that we work with low pressure so that the majority of the atoms travel from the target to the substrate without suffering collisions, so they are traveling in ballistic regime. And let's assume glancing angle deposition. So we have an oblique deposition, an oblique incidence of the atoms. So the first atoms arrive randomly at the surface, and the next atoms have a certain probability of being placed on top of the initial one. And when they do that, they create a shadow region behind them that is stained here in gray, because if all of the atoms are coming with this direction, they cannot be placed onto the shadowed regions. And that's how a competitive growth takes place, and only the atoms that are deposited onto the mounds are finally producing the pillars, and only the pillars with similar height and those that are higher are those that at the end continue to develop, because the low mounds finally are in shadowed regions. So that's why at the end we can obtain an homogeneous growth of the nanopillars. So in order to have tilt pillars, we just need to tilt a lot the substrate with respect to the target, and we will have pillars that are tilted towards the direction of the atoms. If we want to obtain vertical pillars with respect to the substrate, we need to rotate the substrate. If we rotate while we are depositing with this oblique incidence, we will have vertical pillars. So this is the first case, just tilt pillars, obtained just tilting the substrate. You can see that was the direction of the atomic flux during the deposition, so the nanopillars are tilted towards that direction. This is a top view image, this is a cross section, and the material is iron. Well, of course, when we remove the sample from the vacuum, the outer shell, the outer part of the pillars become oxidized. So we have a small peak in X-ray of oxide that is coming from the outer shell of the nanopillars, whereas the core of the nanopillars is made of iron. And we can see that in the top view we have an asymmetry in the plane of the substrate. So when we measure hysteresis loops, this is what we get. We have applied the field in the plane of the substrate along two different directions, in black along the atomic flux direction, and in red orthogonal to it. And you can see that they exhibit different hysteresis loop. And in fact, the one in the transverse direction is harder. And this is due to the fact that in this transverse direction, there is no atomic shadowing, so that the nanopillars can become wider along that direction, and then some coalescence takes place, and as a result, an effective magnetic anisotropy develops. So when we perform micromagnetic simulations that you can see here on the right, we needed to introduce this anisotropy in order to mimic more or less the experimental loop by simulating just a single nanopillar. We try to see if we could obtain loops similar to those experimentally obtained by assuming dipolar interaction by the nanopillars, but we couldn't. Only when we introduced this effective anisotropy, we could mimic the behavior. If we now focus our attention when the field is applied perpendicular to the substrate in the vertical direction, you can see that we have a low remanence. However, if we prepare vertical pillars, this is something that we can do, as we saw previously, by rotating the substrate while we are having this glancing angle deposition. You can see in the cross section that the nanopillars are vertical, and from the top view you can see that now all directions in the plane of the substrate are equivalent. So when we measure the hysteresis loop, we don't see any anisotropy in the plane of the substrate. All directions are equivalent. And in the vertical loop, you can see that some squareness appear. Now we have higher remanence than in the case of the tilt nanopillars, which is coming from the vertical shape of the nanopillars. And we can do some funny things, for instance, using a collimating mask in the shape of a tunnel on top of the substrate while we were depositing. So we deposit from one, we will alternate in the deposition from one side of the tunnel and from the other side. And by so doing, we can create vertical nanopillars which are asymmetric in the plane of the substrate because they are elongated along the direction of the atomic flux. So they have the shape of inverted cone, truncated cones with the ellipsoidal base. And in this case, now we have an anisotropy in the plane, different loops depending on the direction. And in the vertical, when we apply the field in the vertical direction, the squareness has increased and we have a higher remanence than in the previous cases. So the take-home message is that we can tailor the magnetic properties with the morphology. So with this, we arrived to the end of the talk. Let me summarize. We have seen pattern antidotes exhibiting low energy and high energy superdomain walls, and in particular, high energy superdomain walls accumulate a lot of magnetic poles, and they are quite important when we use antidotes for magnetic separation. We have seen that T-shaped nanostructure can be used to store 2 bits of information, and we have seen that we can fabricate nanopillars with different morphologies using a spattering in glancing angle configuration, and as a consequence, we can obtain different magnetic properties. I would like to thank the co-authors of these 3 works that were coming from 4 different countries. In Greece, the Democritos Institute, especially Andreas Kaidatsis. In Chile, the University of Santiago de Chile. In Brazil, 3 different institutions, Unicamp in Campinas, CBPF and UFRG in Rio de Janeiro, and in Spain, the National Research Council and the Complutense University. And at last, but not least, I would like to thank the organizers of this event, and especially all the attendees in Kyiv. 2 years ago, I was in a conference in Ukraine, in Odessa, and I enjoyed the conference, and I enjoy the atmosphere and the nice people and beautiful buildings and the beautiful opera. I went to the opera there, and it was quite shocking to see a few weeks later that beautiful building surrounded by barracks due to the unfair Russian aggression. So I would like to send my support to the Ukrainian people, and as we say in Spain, vamos, Ucrania, vamos. Thank you very much.